A conceptual understanding of one-way ANOVA. The purpose of one-way ANOVA is to test whether sample data come from populations with the same mean or from populations where at least one mean is different from the others. To make this decision, we compare the variability among the sample means, called the between sample variability, to the variability within each sample, called the within sample variability. If the between sample variability is large relative to the within sample variability, this evidence suggests that the samples come from populations with different means. So that's sort of the understanding. We have this two different types of variability. We have the between sample variability and we have the within sample variability. If the between sample variability is large in comparison to the within sample variability, that probably means that the samples come from populations with different means. That's the idea. So the way we're going to calculate the ANOVA test statistic, which is called an F test statistic, it's going to be based on an F distribution, which we'll talk about a little bit more shortly. So the analysis of variance F test statistic is given by F naught. So we're using the same notation as before. The test statistic is F sub 0, F naught, and that is equal to the between sample variability divided by the within sample variability. So we're going to be looking at that ratio of the between sample variability and the within sample variability. That gives us the F statistic. And we're going to compare that to critical values, or we're going to find the p-value, one of the two. Otherwise, the way we conduct the test is pretty similar to the way we've conducted other hypothesis tests. So how do we go about computing this within sample variability and this between sample variability? Well, that's sort of maybe the most complicated part of this. So computing the F test statistic. The computation of the F test statistic is based on mean squares. A mean square is an average or a mean of squared values. For example, any variance is a mean square. So if you'll remember when we calculated variance, the formula for calculating variance is that we take each data value minus the mean and we square that. We add that up and we divide by, well, in this case, n minus 1, the degrees of freedom. So that's the formula for calculating the sample variance. Whereas population variance was the same idea. We take each data value minus the population mean, square it, add them up, and divide by the size of the population. So I'm finding an average of the mean squares. So the differences between the data values and the mean, that's the mean squares. You find an average of that, that is the mean squares. So variances are mean squares. The quantity sigma of x sub I minus x bar squared is called the total sum of squares, or SS total. So sum of squares, SS, represent the same thing. So SS stands for sum of squares, and it is the total sum of squares, and that's what this is. It represents the total variability about the mean of the entire set of data, x bar. The variability within each treatment group is a weighted average of the sample variances from each treatment or sample, where the weights are based on the sample sizes. This estimate of sigma squared is called the mean square due to error, or the MSE. To find the mean square due to error, the MSE, first compute the sum of the squares due to error, or the SSE. So now this sounds very complicated. It's really not. Basically, we're going to be finding a weighted average. So the first thing we have to do is we have to find this mean squares due to error. And in order to find the mean squares due to error, we need to find the sum of the squares due to error. So to find the sum of the squares due to error, we're going to take the sample size minus 1, that's the degrees of freedom, times the sample variance, which is the standard deviation squared. So for the first sample, we're going to take the sample size, which is N1 minus 1, and we're going to multiply that by S1 squared, which again is the variance of the first sample, or the standard deviation squared. Then we're going to do the same thing for the second sample. So N2 minus 1, that's the sample size minus 1, or the degrees of freedom, times the sample variance, which is the standard deviation squared. And we're going to do that for all of the samples. So we're just going to find that and add it all up. Now, the total degrees of freedom for the sum of the squares due to error is the sum of the individual degrees of freedom. I've denoted that by DFE. This is not notation from the textbook, and it's not really standard notation. This is just my own abbreviation for writing this. So the degrees of freedom concerning the error. And so that comes from just adding up all of the degrees of freedom from all of the samples. So that's just going to be N1 minus 1 plus N2 minus 1, and so on to Nk minus 1. Well, if you add all of those up, N1 plus N2 plus so on up to Nk, that's just going to equal N, which is the total number of sample values. So N that I have right here is equal to N1 plus N2 and so on. So that's just like the total size of all of the samples combined, minus K. K is going to be the number of samples that we're dealing with, because that K is coming from all of these ones. So 1, 1, 1, and so on. There's K of them. So we're going to be subtracting off 1 K times. So we're really subtracting off K. So the thing to remember is that the degrees of freedom due to error is going to be just N minus K, where N is the total number of data values in all of the samples. So again, N equals N1 plus N2 and so on plus Nk. The mean squares due to error is an unbiased estimator of sigma square, whether or not the null hypothesis of equal means is true. So the mean square due to error is going to give us a very good approximation of what the population variance is, even if the null hypothesis is not true. So whether it's true or not true, that's going to give us a pretty good estimate of sigma squared. Now, in order to find the mean square due to error, we're just going to take the sum of the squares due to error. So we're going to take this calculation, and we're going to divide that by the degrees of freedom due to error, which is, again, the N minus K. So the sum of the squares due to error, that was this thing, okay? And then the degrees of freedom due to error, that's N minus K. So we're just going to take this calculation divided by this calculation, and that gives us the mean square due to error. And again, the mean square due to error, the significance of that is an unbiased estimator of the population variance. Now, the between sample variability estimate of sigma squared is called the mean square due to treatment, or the MST, since any differences in the sample means could be attributed to the different levels of the treatment. To find the MST, we first compute the sum of the squares due to treatment, or the SST. Now, the sum of the squares due to treatment is the sum of the squared differences between each sample mean and the overall mean, where each squared difference is weighted by the sample size. So we're going to do the same kind of thing. We're going to calculate the MST, the mean square due to treatment. So we do that first by finding the sum of the squares due to treatment. And the calculation for that is, we're going to take the sample size for, say, the first sample, and we're going to multiply that by the difference between the mean of the first sample and the overall mean of all of the samples. So we're going to take x bar 1 minus x bar, and we're going to square that. Then we're going to take N2, and we're going to do the same kind of thing. We're going to take the mean from sample 2 minus the overall mean and square that, and so on. Since the k-sample means and the SST measures how these vary from the overall mean, this sum of squares has k minus 1 degrees of freedom. And again, this is my personal notation, DFT. That is the degrees of freedom due to treatment. So again, the degrees of freedom due to treatment is going to be K minus 1. K is the number of categories. So the MST is going to equal the SST divided by the degrees of freedom due to treatment. So that is going to equal this calculation divided by the K minus 1 degrees of freedom. So the mean square due to treatment is an unbiased estimate of sigma square only if the null hypothesis of equal means is true. So if the null hypothesis is true, the MST and the MSE should be close in value. They should be approximately equal. However, if the null hypothesis is false, the MST will overestimate sigma square and the MSE, because at least one of the sample means in a treatment will be far away from the overall mean. So if the null hypothesis is false, the MST is going to be bigger than the MSE. And so that will show up in our calculation. So again, the F-test statistic, we've already said that F0 is equal to the between sample variability and the within sample variability. Well, the calculation for the between sample variability is going to be the mean square due to treatment. So the MST is this between sample variability. That's what the MST is measuring. It's the variability between the different samples. And then the mean square due to error, that's the within sample variability. So really, the way we're calculating the F-test statistic, the way we're calculating F0 is by taking the MST, the mean square due to treatment, and dividing it by the MSE, the mean square due to error. So, computing the F-test statistic by hand. Step 1, compute the sample mean from the combined data by adding up all of the observations and dividing by the number of observations, and call this value X bar. So this value X bar is the mean of all of the data across all of the samples. So like, for example, in our lean meat, mixed meat, high fat meat problem, we had 8 data values in each group. So altogether, there's 24 data values. If I find the mean of all 24 data values, that is X bar. Step 2, find the sample mean for each sample or treatment. So we're going to let X bar 1 represent the sample mean of sample 1, X bar 2 represent the sample mean of sample 2, and so on. So again, X bar 1 would be like the mean of just the 8 lean meat sample. X bar 2 would be the mean of just the mixed meat sample. And X bar 3 would be the mean of the high fat sample. Step 3, find the sample variances for each sample or treatment. So S1 squared represents the sample variance for sample 1. S2 squared represents the sample variance for sample 2, and so on. So again, if I take the sample variance of the lean meats, the sample variance of the mixed meats, and the sample variance of the high fat meats, that would be S1 squared, S2 squared, and S3 squared. Step 4, compute the sum of squares due to treatment, or the SST, and the sum of squares due to error, the SSE. Step 5, divide each sum of squares by the corresponding degrees of freedom, K minus 1 and N minus K respectively, to obtain the mean squares due to treatment and the mean squares due to error. So we have to do these calculations. We got to find the SST and then use that to find the MST. We got to find the SSE and then use that to find the MSE. And then once we have that, we can compute the F-test statistic. So for the previous example regarding the daily consumption of calcium for children who exclusively use lean meats, mixed meats, or higher fat meats, compute the F-test statistic. So Back here, we set up our null and our alternative hypothesis, and we verified that we can conduct an ANOVA test. Now we're going to calculate the test statistic for the ANOVA test. And then once we do that, we'll talk about how we go about concluding the ANOVA test. So in order to calculate this, the first thing I'm going to need to do is I'm going to need to find the overall mean. Now, I can calculate the overall mean a couple of different ways. I'm going to come back to StatCrunch here. So again, I have the data here in StatCrunch for the three groups. One way that I could find the overall mean is that I could just find the mean of each of the groups, and then I could find a weighted average of that. So if I go to stat and summary stats and then columns, and if I select my three groups and say compute, then I have here the mean of each of those groups. And I'm going to write those down on my paper. So for the lean meats, the X bar for the lean meats is equal to 794.7625. X bar for the mixed meats is 898.5375. And the X bar for the higher fat meats is 829.2375. And again, I got those all in StatCrunch. Now, again, the first thing I'm supposed to do is find the overall value of X bar. Well, and then I'm supposed to find each of the individual X bars. Well, I kind of went out of order on that, but I'm going to use these values in order to calculate the overall X bar. So to find the overall X bar, I can take the number of data values for lean meats, for example, that's 8, and multiply that by the 794.7625. What that would do is that would give me the total of when I add up these 8 data values. And then I'm going to do the same thing if I take 8 times the 898.5375. That's going to give me the total of when I add up these 8 data values. And then if I take 8 times the 829.2375, that would give me the total of when I add up these 8 data values. So if I do this, that's going to give me the total of when I add up all of these data values. And if I take that sum and divide by 24, which is 8 plus 8 plus 8, so altogether there's 24 data values, that will give me the mean. So if I take 8 times 794.7625 plus 8 times 898.5375 plus 8 times 829.2375, that is 20,180.3, and that's going to get divided by 24. Divide by 24, so that is 840.8458333, and I'm going to just round that. Now, rounding is going to give me a little bit of error, but I'm going to round that to 840.846. I'm going to round that to 3 places. Now, if I'm using StatCrunch, another way that I could also calculate that is I could just copy all of these data values into another column. So I just put all 24 data values into a single column. So I could do that, and then I could do stat summary stats for columns, and I could just pick that column And if I do that, then the mean that I get, 840.84583, that's the same mean that I got by doing it by using the samples. Now, so I have done step 1 and I've done step 2. So I know X bar and I know each individual X bar. Step 3, I need to find the sample variance for each of these sample groups. So again, what I need to do now is I need to find the sample variance for the lean meats. I need to find the sample variance for the mixed meats, and I need to find the sample variance of the high fat meats. And I just want to say a word of caution about this. So a lot of times students find the standard deviation instead of the variance. You have to have the variance here, which is the square of the standard deviation. So like if we were to calculate these standard deviations on our calculators, then you're going to have to square the standard deviation to have the variances. If you use StatCrunch, you could also get the standard deviations and square that to get the variance, but you can also just get the variance directly from StatCrunch. So I'm going to come back to StatCrunch again, and I'm going to calculate the sample statistics for the 3 different groups. So I have that here. So right here, I have the 3 variances. The variance for the lean meats is 1,153.688. For the mixed meats, 1,632.080 if I round to 3 places. And for the high fat meats, 1,512.060 if I round to 3 places. So I'm going to come back to my page here and write those down. And again, it's the variances that I want, not the standard deviations. But if you have the standard deviation, you can square it. So again, that is for the lean meats, the variance is 1,153.688 approximately. Again, my rounding is going to give me a little bit of error in my F statistic, but it's not going to be significant. The variance for the mixed meats is 1,632.080 if I round to 3 places. And for the higher fat meats, the variance is 1,512.060. So I've done step 3. Now I need to compute the sum of the squares due to treatment and the sum of the squares due to error so that I can find the mean squares due to treatment and the mean squares due to error. So step 4, I'm going to find the SST and the SSE, and then I'm going to use those to find the MST and the MSE. And so I'm going to use these values in order to be able to do that. So I'm going to pull back in my notes. Let's calculate the SSE first, and then I'll calculate the SST. And then once I have those, I'll calculate the MSE and the MST. So to find the SSE, now again, what I do for the SSE is I take each sample size minus 1 times the variance of the group, and I'm going to add that all up. So in this case, for the SSE, I'm going to take the sample size minus 1, so that's going to be 8 minus 1, or really 7, times the variance for the first group, which is again the lean meats. So that's going to be 1153.688. And I'm going to do the same thing for the other groups. So the sample size for the mixed meats is 8. So I'm going to take 8 minus 1, or 7, times the variance, which is 1632.080. And I'm going to do the same thing for the third group. So 8 minus 1 times the variance, 1512.060. Now, when I punch this in my calculator, I'm going to not type 8 minus 1. I'm going to actually type 7, which is what it is. So I have 7 times the 1153.688. So 7 times 1153.688 plus 7, again, 8 minus 1 is 7, times 1632.080 plus 7 times 1512.060. And that is 30,084.796. So that's the SSE, the sum of the squares due to error. And again, what that is doing is that's measuring the within sample variability. Now I'm going to calculate the SST, the sum of the squares due to treatment. So again, the formula for that is I'm going to take each sample size times the sample mean for that group minus the overall sample mean squared. And I'm going to do that for each group and add that up. So for the first group, the sample size is 8. The mean for that group is 794.7625. The overall mean was 840.846. And I'm going to square that. Plus the same for the second group. So the sample size is 8. The individual mean was 898.5375, and the overall mean 840.846. Whoops. 840.846, and that gets squared. Plus, for my third group, for the higher fat meats, the individual mean, well, first of all, we have a sample size of 8. The individual mean is 829.2375 minus the overall mean 840.846 squared. So again, this is going to give me the sum of the squares due to treatment. So 8 times parenthesis 794.7625 minus 840.846 close parenthesis squared plus we have 8 times parenthesis 898.5375 minus the 840.846 close parenthesis squared plus 8 times parenthesis 829.2375 minus 840.846 close parenthesis squared. And that gives me a total of 44,694.043 if I round to 3 decimal places. So this is approximately 44,694.043. That's a decimal point, this is a comma. So I now have calculated the SSE and the SST. So I'm going to divide each of those by the appropriate degrees of freedom in order to get the MST and the MSE. So over here on the side, I'm going to go ahead and write down the degrees of freedom due to error. That is equal to N minus K. So in this case, we have a total of 24 data values. That's the N. And we have 3 groups. So minus 3. So there are 21 degrees of freedom due to error. And the degrees of freedom due to treatment, that is equal to, again, K minus 1, the number of groups minus 1. So that's going to equal 3 minus 1 because we have 3 groups. So that's going to be 2. So the MSE, the mean square due to error, is going to equal the 30,084.796 divided by the degrees of freedom due to error, which is 21. Again, that's N minus K. The MST is going to equal the 44,694.043 divided by the degrees of freedom due to treatment, which is 2, K minus 1. So if I do those calculations, 30,084.796 divided by 21, I'll write that down in just a second, 1,432.609, and 44,694.043 divided by 2, so that's 22,347.0215. So this is going to equal 1,432.6093, and this is 22,347.0215. So I have the mean square due to error, and I have the mean square due to treatment. So last but not least, to calculate our F statistic, I'm just going to take the MST divided by the MSE. So F naught is going to equal the 22,347.0215, that's the mean square due to treatment, divided by the 1,432.6093, the mean square due to error. And that's going to be approximately 15.599 if I round to 3 places. So for our calcium consumption problem, for the different groups of children who eat only lean meats or only mixed meats or only higher fat meats, the test statistic is 15.599 approximately. So calculating that by hand is a little bit involved. It's not the worst calculation in the world, but there is a lot to it. We just have to do it in stages. So again, what we're really trying to find is this mean square due to error and this mean square due to treatment. But in order to find those, we have to know like the individual standard deviations, we have to know the individual means, and we have to know the overall mean. So there's like a lot of preliminary calculations that have to be done by hand before we can get to the overall calculation that we need.